All right, now let's look at this concept of splitting that appears in proton NMR, but we don't really look at it much in carbon NMR. And splitting, as I introduced in a previous video, gives us information about the number of adjacent hydrogens. So what I'm going to do is go through what is happening, and then I'm going to talk about the why. Okay, so let's first look at this structure here. And just for the sake of time, I'm going to label these as A hydrogens. They're equivalent to each other. I'm going to label these as B and these as C. Now, what I want you to do is look at the A hydrogens. And you want you to look one carbon over in all directions. Well, for that, that's only this way. There are no hydrogens next to those A hydrogens. So let's just kind of write that down. No adjacent hydrogens. Now let's look at the B hydrogens. If I go one atom one way, that's an oxygen, no hydrogens there. If I go one atom the other way, there's three more hydrogens. So B is adjacent to three hydrogens. And I want to highlight something important here. Those three hydrogens are not equivalent to B. And then let's look at the C hydrogens. All right, there's nothing on one direction to the right, but if I go to the left, I do hit an adjacent carbon with two hydrogens. So C is adjacent to two hydrogens. And again, I want to emphasize that those two hydrogens are not equivalent to C. Now, the rule that we use to predict what the splitting is going to be is simply the n+1 rule, which is basically n is the number of adjacent hydrogens that are not equivalent. So if I use that n+1 rule, and let's go through A, B, and C. So I said for A that there's no adjacent hydrogens on A. So n would be 0. So according to the n+1 rule, I would just see one peak. If B is adjacent to three hydrogens, I plug that 3 into the n+1 rule, I would see 4 peaks. And C is adjacent to two hydrogens, so I plug that 2 into the n+1 rule, and so for C would show up as 3 peaks. Now, if I take a look at the proton NMR, and I look at, let's look at, just kind of go from left to right here. The signal at 4, what hydrogen do you think that represents? The one with the highest chemical shift. Well, it's going to be the ones that's next to the most electronegative stuff, which are B hydrogens. And if you look at it, it's split into 4 peaks. I'll kind of draw them a little bit bigger here. We call this a quartet. We use like in a lowercase q. And then what will be our next highest chemical shift here? The one at 2? Well, that's kind of like where our hydrogens alpha decarbonyls appear. And so that's hydrogen A. Notice A is just a single peak. It's not split into anything because it's not adjacent to anything. And so we call this a singlet. And we'll use the lowercase s to denote that as like a shorthand. And then the last one here by process of elimination. What's the farthest away from all this stuff? Just a regular hydrogen on an sp3 carbon that's going to start around 1 or so. And that's our 3C hydrogens. And notice it's split into 3 peaks. I'll draw it a little bit expanded here. Oops. And we call this a triplet. Use the lowercase t for that. Now I've kind of gone over the how you go about this. Okay, you look for adjacent hydrogens that are not equivalent to the original hydrogen. And you just kind of add it all up and use the n+1 rule. Now let's talk about the why. Why is this going on? Remember at the very beginning, I wanted you to treat these nuclei as if they were bar magnets. And if you've ever played with magnets, and let's say you hold on to them tightly and you bring them close together. You don't let them like stick, or you bring them close together. What do you start to feel? You start to feel the magnetic fields of them interacting. Either you feel the attraction pulling your hands together, or the repulsion pushing them apart. And that is kind of what's going on with adjacent hydrogens because they are close enough together. This is why we only look at adjacent. We don't go any farther than that. When they are close together, you have the magnetic field of one of those hydrogens interacting with the magnetic field of the other hydrogen. This is known as what is called spin-spin coupling. It's the interaction of two nuclear spins getting close together. And so essentially, as I said before, splitting tells us about the number of adjacent hydrogens, right? Using the n+1 rule. So let's kind of get in the nitty-gritty of why the n+1 rule works. Okay, so let's look at, we're going to focus on the A hydrogen here. And it's adjacent to just one other hydrogen, the B hydrogen. And what happens is that B hydrogen could either be aligned with the magnetic field, so that big, powerful electromagnet, or it can be aligned against it. And those two things have slightly different chemical shifts, like very, very, very slight. And so if A interacts with this kind of B, we get one split. If A interacts with this other B, we get a different kind of split. But we treat it as one signal. And so if it's split into two peaks, we call that a doublet. So we didn't see an example of that before, but that is what a doublet looks like. And the reason they're of equal height is because this is just as likely as this. Now let's get a little bit more complex. Let's look at an A hydrogen next to two B hydrogens, and we'll look at them like going in one direction, or it is also quite possible that the B hydrogens are not on the same carbon. Now, in this case, there are three possible combinations. Either the B hydrogens, both of them are aligned with the magnetic field, both of them are against the magnetic field, or one is with it, one is against it, and vice versa. So there's three possible combinations of A interacting. And so if A interacts with these two B hydrogens that are going with the field, we get one signal. If it interacts with the other B hydrogens going against the magnetic field, it gets another signal. And then if it interacts with these, then we get a third signal. Now we lump all three of those into one, and this ends up being a triplet. Now notice that there are twice as many instances here of 1B going one way and 1B going the other way. And that's why this middle peak is twice as high as the outside peaks. And then finally, a quartet. So we have the instance here where we have an A hydrogen next to three hydrogens, three B hydrogens. We could also have this same situation where we have maybe two on one side. Well, no, I don't want to get into that quite yet. Okay. And so there's a lot of different possible combinations. So we have one combination where all three B hydrogens are aligned with the field, all three are aligned against it, and then a bunch of combinations where two of them are aligned with it, one are against, and vice versa. And so, again, going through this exercise, if A interacts with these, then we get one signal. If A interacts with these, we get another signal. And then if it interacts with these, that leads to the two signals in the middle. And that leads to a quartet. Now, it is possible for there to be higher than quartets. So let me give you an example here. And let's assume all the B hydrogens are equivalent to each other. How many hydrogens are adjacent to A? Well, if I go that way, there's two hydrogens adjacent. And this way, there's two hydrogens adjacent. So if I use the n+1 rule, that means I should get a signal split into 5 peaks. Pretty much anything 5 or more, we just call it a multiplet and use the letter M for it. Even though it would look something like this, we just start to call them multiplet. And you can actually, depending on the quality of the NMR, you might be able to see the resolution enough to look at that and say, oh, wait, there's 1, 2, 3, 4, 5 peaks there. If I use the n+1 rule, I know that that hydrogen has to be adjacent to 4 other hydrogens. Imagine this could get super messy if you had a hydrogen that had something like this. Because this A hydrogen is adjacent to those three and these three, and then those three as well. And, if you don't have a great quality NMR, it's just going to look like a big mess. But we'd still just call it a multiplet. All right, so let's look at some examples here. So here is the structure for methyl benzoate. Don't look at the NMR quite yet. Let's just kind of go from the basic, foundation here. Let's just predict the number of signals we should see. Okay, I'm going to draw in all the hydrogens here for benzene. And I'll start here at this methyl group because it's sp3 hybridized and it's all, it's the only sp3 hybridized carbon around. And then let's take a look at our benzene. So we got a B hydrogen there. Do you see any others that look exactly like B? Notice like if I draw a line through, there's symmetry there. So those two are going to be the same. These two are going to be the same. And then there's that one. Now let's do some predicting. First of all, let's predict some approximate chemical shifts. So A, the chemical shift should be, well, it's next to an oxygen. It's also a little bit, one more down is a carbonyl. So I'm going to say probably a little bit higher than 3.5, but let's start at 3.5 and see. And then B, C, and D should probably be somewhere around, you know, 6 to 8. I'll just say 7 to 8 here. It's typically where benzene hydrogens are. So that's where they should show up. Now that we've talked about splitting, let's predict the splitting. So let's look at the A hydrogens. Are the A hydrogens adjacent to any other hydrogens? Now, if I go one atom over, it's just an oxygen. So no adjacent hydrogens. I'm going to say a singlet. You might look at that and say, well, wait a second, there's 3 A hydrogens. Yeah, and they all have the same exact chemical shift. The splitting only arises from adjacent hydrogens. We should see an integration. In fact, let's write that down. Our integration ratio should be, somewhere around 3 hydrogens. And then let's look at our B hydrogens. Well, it doesn't matter which one you pick. Okay, I'll just look at the one on the top. This B hydrogen is directly adjacent to one hydrogen, the C hydrogens. So I'd expect B to show up as a doublet. And there's 2 B hydrogens, so my integration should be somewhere around 2. Now let's look at our C hydrogens. Okay, C is, got to look carefully. I got one hydrogen adjacent that way and one hydrogen adjacent that way. So C should show up as a triplet. Now I'm going to put this in quotes, and I want you to see something here. I'm not going to go much farther into this, though. Notice that B and D are not equivalent to each other. So C will probably show up as a weird looking triplet. If B and D were the same, then we'd see a nice, like perfectly symmetrical triplet. But because it's not, it's going to look weird, and I'm not going to go farther into that, but just kind of you'll see it when we put it all together. And then there's 2 C hydrogens. I expect an integration of 2. And then D, notice D is adjacent to a C on that way and adjacent to C on the other way. So that would show up as a nice triplet. And there's 1 D hydrogen, so I should see an integration of that. Now let's go look at our NMR. Okay, so just like I predicted for A, there should be a signal somewhere around 3.5 or so. It's a little bit more, that's fine, but somewhere where I predicted. And I also predicted that it should be a singlet. And look at that, its integration is 3 as well. Now let's look at our B hydrogens. Okay. Um, Before I kind of focus in on that further, look at B, C, and D. Which do you think should have the higher chemical shift between B, C, and D? Well, the B hydrogens are closer to this group here. And so they should have a little bit higher of a chemical shift. And so if I look at that, there's my B hydrogens there. And they kind of look like a doublet. It can't really zoom in much or else it gets a little too messy, but you got a nice little doublet there. And an integration of 2. Now, this is where things get a little kind of interesting because I predicted I should see 4 signals, yet I only see 3 sets of peaks here. That's because this signal here is hiding, not hiding, but is both C and D. And if we imagine what those look like, if C is a triplet or a weird looking triplet, and D is a triplet, and they have a very similar chemical shift, that looks like a big mess. And that's what we kind of see there. So because they're so close together in chemical shift, they're overlapping. And what looks like one signal is actually 2 separate signals that are overlapping. And that's why the integration is 3, because there are 2 C hydrogens and 1 D hydrogen. All right, let's look at another example. So let's draw out propylbenzene here. And let's start from the basics and just predict first how many signals we should see. Well, let's start up here at the top. That's a CH3. No other CH3s around, so it's unique. Here's a CH2, but this one is a CH2 as well. Can I call them equivalent? Hopefully, you're yelling at your computer screen right now that those are not equivalent because this B is closer to the CH3, and this one is closer to that benzene than B is. So I'm going to call that something different. And then I'm going to draw in the benzene hydrogens here. And because of symmetry, these 2 are the same, these 2 are the same, and that one is unique. Now let's start doing some predictions. A is kind of a primary carbon, nothing remarkable around it, just more carbons. And so I'd start to look for it around 1 ppm. And if I were to predict the splitting of A, how many hydrogens are adjacent? So again, I'm just going to go 1 carbon over. How many hydrogens are there for B? There's 2. So I'd expect it to show up as a triplet. And then let's look at B. Okay. B is still kind of a regular carbon, nothing remarkable directly around it. It is secondary though. So I'd expect it to be a little bit higher than A. So I'm just going to approximate to be maybe 1.5 or so. And how many hydrogens are adjacent to B? Again, I'm going to go 1 carbon in each direction. So I go this way, there's 3 hydrogens. I go this way, there's 2 hydrogens. So that's a total of 5 adjacent hydrogens. If I put that into n plus 1, that's going to be, 6. I'm just going to call it a multiplet. And because A and C are not equivalent, it's going to look weird. It's not going to look very symmetrical. All right, now let's look at C. Now C is interesting because it's benzylic. Not only that, it's got extra carbons like B and A around it. So normally benzylic starts at around 2-ish, 2.1. I'm going to say maybe a little bit higher than that because of the extra carbons. And how many hydrogens is C next to? Well, it's got just two on one side and nothing on the other side. So C should show up as a triplet. I kind of marked these incorrect. Let me fix these. These should be B, D, E, and F. Sorry about that. All right, D, E, and F are all aromatic. I'd expect D to be a little bit higher than E and F, but somewhere between 7 and 8. Same thing for E and F. D is next to 1E, so it should show up as a doublet. E is next to a D and an F, so it's going to be a weird looking triplet. And F is next to 1E on one side and 1E on the other, so it's going to show up as we'd expect a fairly symmetrical looking triplet. Now let's go to the actual spectra. A would have the lowest chemical shift. We predicted somewhere around 1, and that's exactly where we see it. And if we look at it, we got a triplet there. Integration of three hydrogens. Then we said B should be a weird looking multiplet and somewhere around 1.5, which is exactly where we find it. So notice there, you know, what is that, like 1, 2, 3, 4, 5, 6? Yeah, that's a multiplet. And then we predicted C should be somewhere around 2.5, and there it is, just above 2.5. And it's a pretty nice looking triplet as well. Now, if we go to benzene, again, we got something weird going on. It looks like one signal, but it is actually a combination of D, E, and F, which is why the integration says 5. This is the same kind of thing that happened with our previous example, where they are so close in chemical shift. We got a doublet in one case, we got a weird looking triplet in another case, and then we got a regular triplet here. And if you look at that, that kind of looks like that big mess that we see right there. Now, one of the ways that I know that all 5 of them are overlapping is because the integration is 5, which is all of my aromatic hydrogens. Now, to finally wrap up this splitting stuff, I do want to kind of backtrack a little bit and talk about sometimes we can do splitting in carbon NMR. Most of the time, most carbon NMRs that you will see, they are proton decoupled, meaning the NMR doesn't see hydrogens. Once in a while, we can do a proton coupled carbon NMR and hopefully it doesn't come out too messy. So if it's proton coupled, then the carbons are split by the hydrogens, and I want you to circle, highlight, star this phrase. They're attached to that carbon and not adjacent. So big point number 1 here is splitting in carbon NMR is different than splitting in proton NMR. So a singlet in carbon NMR is a carbon with no hydrogens. A doublet is a carbon with 1 hydrogen. A triplet is a carbon with 2 hydrogens, and a quartet is a carbon with 3 hydrogens. Now, those don't always have to be sp3 hybridized. They can have a variety of hybridizations. This obviously can only be sp3, but there are instances where a CH2 could be sp2 hybridized. And there are instances where a CH could be sp hybridized, like maybe a terminal alkyne, sp2 or sp3. And we could say the same thing for a carbon with no hydrogens. sp, sp2, or sp3. So let's look at a couple examples and then we will call it a day with this series of videos. So I'm going to revisit some problems we did in the past. So here's 3-bromo-2-butanone. And what I'm going to do is add the splitting to these. So we have singlet, doublet, quartet, quartet. If we come down to the structure of 3-bromo-2-butanone, notice that signal at about 200, that is blatant like carbonyl carbon. That's our singlet because it doesn't have any hydrogens on it. The next highest chemical shift would be the carbon with the bromine on it. It has one hydrogen on it. I'll draw it in here. And that's why it shows up as a doublet. And then these two methyl groups are our quartets because they have 3 hydrogens on them. If we go back and revisit 1-pentyne, I'm going to label these down here. Singlet, doublet. These are triplets, and that's a quartet. So in the last time we did this example for 1-pentyne, we said that these were our carbon-carbon triple bonds here. And so this one has to be our singlet because it doesn't have any hydrogens on it. And this one has to be our doublet because it has a terminal hydrogen, just a single one on it. And then these are our 2 triplets, and that is our quartet. Now, you might not always see splitting for carbon NMR. So if it's supposed to be there, I'll give it to you. If it's not, then don't worry about having to interpret it. But that's going to conclude the required notes that you're going to have to take. I am going to record another video. It'll be rather long because I'm going to do a bunch of examples where we're using multiple types of spectra to predict or determine the structure of some unknown compound.